the intermediate code and you go straight to the target language. But best practice is that you can plug in an optimizer before you generate the final code, and even after the final code is generated, it is possible to optimize the target code. So as much as it's optional, it's good to understand what it entails. And basically, code optimization is a program transformation technique which we use to try and improve the code. And why are we doing this? We want to make it consume less resources. So for instance, CPU, memory usage, etc. And as well deliver high speed. So we're looking at the code we're generating and asking, is this the most efficient use of the resources available to us in terms of the particular architecture? Are there some redundant expressions? Basically stripping off things that are not important, but that do not affect the meaning of the program. Okay. So in optimization, high-level programming constructs are replaced by very efficient yet low-level programming codes. Now, the three requirements or the three rules that must be observed when we are doing optimization. Number one, the meaning must be preserved. Yeah, so the output code must not in any way change the meaning of the program. Then secondly, the optimization should increase the speed of the program. And if possible, the program should demand less resources. Okay, so you're not going to say optimizing, yet you're slowing down the time that the new code is taking compared to the unoptimized code, and that is not necessary. Yeah, so speed up must occur, as well as better use of resources where possible. And then the work done must be worth the effort. So in other words, there's no need of doing optimization if it doesn't yield more efficient and faster executing code and less resource hogging code. Yeah. So the optimization should itself be fast and also should not delay the overall compiling process. So here we are saying that, in fact, that would be like the fourth rule, that optimization as a stage, remember it's optional. So if you're plugging it in, it has to be done very, very fast so that it doesn't slow down the compile time for the program. Okay. So it should not delay the overall compiling program. Now, the opportunities for performing code optimization are at three levels. So first, there's at the programmer level. So here at the beginning, the users can change, the programmer themselves, the human, can change or rearrange the code or use better algorithms to write the code. And this is why you go through that course on algorithm design. So the whole idea is asking, can we make sure that the programs we write, even before we take them to the compiler, are as efficient as humanly possible, right? So the algorithm that you use, the directives that you use, let's write better algorithms, okay? Then secondly, at the intermediate code level, so after we generate the intermediate code, the compiler can modify this code by address calculations, improving loops, etc. And we're going to focus a lot. In fact, most of the code optimization is done on the intermediate code before it becomes architecture specific. And then finally, there's also opportunity to optimize the target code. And here is that when we're producing the target machine code, the compiler can make use of like figure out how best to use the memory hierarchy, so CPU registers, etc., the cache, just to make sure that the code that is being generated is as fast as possible, so that you reduce like load and stores. If there's a way you can store a particular value in a memory hierarchy or cache, then you do that. Okay. So this is a diagram we've been looking at. We now understand from the source language, you build your scanners, we get tokens, we do parsing, you get your tree, you augment the tree with semantic information, then you generate the intermediate code, and then from there now you can optimize before we generate the final target code. Now the different types of code optimizations. So before this slide, note that there are three. We have what are called high-level optimizations, we have intermediate level optimizations, and low-level optimizations. Okay. So we'll focus more on the intermediate level optimizations, which is what is shown here. But it's good to know that high-level optimization is basically language-dependent type of optimization that we are looking at optimizations that are pretty close to the source language. Okay. So here include like replacing function calls with the function body directly to reduce the number of function calls you can make. Partial evaluation, which reorders the contents of a loop. Just many things that you can do at a high level before you get into the intermediate code. Then most of the code optimizations, as I've said, fall under intermediate code optimization. So the intermediate code optimization, which is language independent. Let somebody in. So intermediate code optimizations are language independent. And the different types of levels within intermediate code optimization is what we call the window or the peephole level, the basic block level, where we have the CFG that is at the procedural level, as well as intra-procedural, where you have different procedures calling each other. And we'll be looking at the different types of optimizations that can be done on the intermediate level. Then lastly is the low level optimization. This one, as you can guess, is very specific to the type of the architecture. Yeah, and here we're looking at register allocation, instruction scheduling, utilizing floating point registers or units as opposed to just the normal, because then you're taking advantage for architectures that have a floating point unit. If you find you're performing a floating point calculation, then you can assign it to the FPU, etc. There's also branch prediction, and we talked about some of these things when we were talking about target code generation. So as we generate the target code, then you can also perform now the architecture-specific optimizations. Then we have two broad categories of optimizations. So those are the levels. We talked high level, intermediate, and low level. The other way is to think about them as machine independent versus machine dependent. Yeah. So machine independent is improving the intermediate code to obtain a better output, whereas machine dependent is done after we've generated the target code. And of course, this is transforming it to better utilize the target architecture, the target machine architecture. So here we'll be talking about CPU registers, absolute memory references, etc. Yeah. So we need optimization because it results in cleaner code and higher consistency. And of course, we're going after efficiency. So we now want to look at each of these, especially for the intermediate code optimizations. So let's start with the peephole optimizations. Now, the peephole optimization, as the name suggests, it's also called a window optimization. And it's focused on very limited. The window size is very small. It could be 1 or 2 statements or 3 statements. So it's within a basic block, and you're looking at a few number of statements and checking what you can optimize over there. So this technique works locally on the source code, transforming it into an optimized code. So you're looking at a small portion of the code. And the peephole optimization technique is target code. So the different types of optimizations at the peephole optimization, one is called constant folding. And as you can see, it's quite obvious what we mean by constant folding. Basically here, what you're trying to do is just, if we have an expression that generates a constant value, then instead of performing that calculation again and again, we calculate it once and we assign it. Yeah. So instead of saying we assign it to 64, so that now you've reduced, you have from 2 operations, you have one or one instruction. Then the other one is eliminating unreachable code. Okay. So reachable code is code that it's also called dead code elimination. So these are one or more code statements which are never executed or are not reachable. Their output is never used. So such program eliminated. So for instance, here, if the jump goes to L2, will never come here. So no need to do this. Don't waste processor time on this calculation, which is not going to be used again. So you eliminate that. Then the other one, we have the flow of control optimizations. And as you can see from the example given, we're basically looking at instances in a code where the program control jumps back and forth without performing any significant task. So these jumps can be removed or rerouted, like you just skip the unnecessary jumps. So for instance, say you have go to L1, then L1 says go to L2. So this simply just, you don't have to do this, you simply just from here go to L2. Yeah, so that's a flow of control optimization. So you can see what you're trying to do. They're looking at very few statements and performing very minor changes, which of course should not change the meaning of the code, but helps in reducing the number of operations that are that are required to be executed. Then we have algebraic simplification. So for instance, something that where you're adding 0 to something, you don't need to do that because we already know that it doesn't change the value of x. So that statement should just be removed. We've talked already about dead code, is a code where the value is not used after it's been assigned. So in this case, we're saying x equals 32, y equals x plus y. We might as well just say y equals y plus 32. So you don't need to assign this x. You don't need this. So just basically use the value of x directly and eliminate the assignment operation. Then very important is a reduction in strength. And this is very, very important because it specifies the operators which can be replaced by an operator which is not as compute intensive. Yeah. So for instance, multiplication and division can be replaced by addition and subtraction, or by using the left shift or the right shift operators. Okay. So for instance, x is assigned x times 2. Instead of doing this, you can use the shift operator or addition. So of course, addition is a less compute intensive instruction compared to times. So these are examples of peephole optimizations where we are trying to ensure that the code is using less resources and executes faster. So peephole optimizations are local in nature, as we've said. They're pattern driven. So you can see the different types of patterns. If you're adding 0, if there's a jump. So there are many patterns that you can look out for. And of course, they're limited by the size of the window. I would say the window, is it looking at 1 statement or 3 statements or 5 statements? So when you're able to look at what's happening in that small section, you're able to figure out what can. For instance, like dead code, you'll be able to see this is not used in the next 3 statements. So it's unreachable and we can eliminate it. So the other level after the peephole is under the basic block level. And here, the kind of optimizations that can be done are what we call the common sub-expression elimination, constant propagation, dead code elimination, and many others. So we have copy propagation, partial redundancy elimination, etc. So this is a common expression which can be eliminated. So when you look at this example, we're saying ai plus 1 is assigned the value of bi plus 1. So if this is our intermediate code, of course, we'll first have to compute I plus 1. So we store it in temporary 1. And then we assign T2 to be the value of B referenced with T1. So BT1, we store it in T2. And then again, we do I plus 1 for the A. And then we assign 8. And sorry, we store the value of I plus 1 in T3. And then we assign that to T2. So we can see here, basically T1 and T3 have the same value. It's a common expression. So you don't need to compute it twice. So we delete it because the value of T3 has not been changed, or rather the value of I has not been changed since this point. So the value of I remains the same. So I plus 1 should just give us T1. So rather than, so you don't need to do this. So we'll have just 3 instructions. So AT1 is assigned T2. So if I is a constant, let's see how we go step by step. So for instance, if this is our first generated intermediate code, I equals 4, T1 equals I plus 1, T2 equals BTI, and then AT1 is equals to T2. So if I is a constant, we don't even need to do I plus 1. So here we'll basically just set T1 to 5, right? And then here, because we already know the value of T1, you don't need to again reference store that value. So you can just simply just have T2 is goes to B5. And you can see now the final code, we have gotten rid of one expression. But as we said, whenever we are doing optimization, we should never change the meaning of the code. So we're still able to do the same thing, but we've gotten rid of an addition and an assignment. Now, we talked about the control flow graph when we're trying to figure out, when we're doing intermediate code generation, so that we're able to figure out branching or just memory utilization. So here we have our CFG. You remember we defined it. Now, when you're looking at optimization, you need to see for a given statement what comes before it and what comes after it. So you're able to figure out, is this a dead code? Is this a common expression? So you need to have a wider view than the people window. So we define two sets in the algorithms for optimization. There's what is called the successor of a particular node and the predecessor of a particular node. So when you look at successor, we have X is one of our vertices or nodes, such that there exists an edge in our CFG, such that uh, this particular edge, V, comes before X. So V is a successor of X, because V, then you go to X. So V is a successor of, sorry, I'm confusing myself. The predecessor, we're focusing on X, right? So if you have an edge, V goes to X, then V, the successor of V is X. And the predecessor of X is V. You're basically asking what statements come before and what statements come after. Okay. And how to use that information? So we need to bring in a new definition, what we call points. And a point is basically any location which is between adjacent statements. So like if you have a particular basic block, it has 4 statements. So between statement 1 and statement 2, that's a point. Between statement 2 and 3, that's another point. So that's one definition of a point. So within between two adjacent statements. And also you have a point before a basic block and after a basic block. Yeah, so we're interested in those particular points. So now we're able to figure out what is being shared, what is dead, what can be eliminated, how can we perform optimization. So we're looking, remember optimization is done algorithmically. So all these definitions help in writing the algorithms for optimization. So once you've understood what a point is, then we define a path in a CFG from point P1 to Pn. So those are points. And we're saying this is a sequence of points that such that for all j, where j ranges between 1 and the last point, either pi is the point immediately preceding a statement, and pi plus 1 is the point immediately following that statement. So we have point 1 and point 2. They come in between a particular statement. So P1 will be before, P2 will be after. Or the second definition of a point was at the beginning of a basic block or after. So Pi is the end of some basic block, and Pi plus 1 is the start of the next block. Yeah. So we're basically trying to figure out how can we identify the points algorithmically. So this helps us have a better view of the points. So this is our control flow graph. Remember, we are saying control passes from this basic block to this one. Here we have a conditional. If C is greater than D, we go this route. If C is not greater than D, we go this route. And then from each of that, so we have our CFG. Now we said, what is a point? So we're trying to figure out what is happening after every statement or between the different basic blocks. So between C and D, we have a point. Between D and I, we have a point. After this basic block, we have a point. And before the next basic block, we have a point. So this is the same Pi, Pi plus 1, or Pi and Pi plus 1. Okay. Then now, what is a path? So you said a path is where you have the successors and the predecessors. So, for instance, along this path, you're able then to figure out for this statement, for instance, like now D is assigned A times C. Its predecessor is this one, and its successor is this one. So now you'll be able to use that information to figure out if before, like, can I, for this particular statement, is my value at all modified by my predecessor, or after my predecessor? That's my successor. So once you have the CFG, you've calculated the points, you've determined the set of successors for each statement, you've determined the set of predecessors for each statement, then now you're able to make the CFG level optimizations. So now these ones must take, of course, control flow into the account, because if you have a branch or a conditional, then we need to figure out where is this going, so that we're able to figure out what optimizations we can do. Yes, Roman.
I have a question about the path on the
Mhm,
previous slide.
mhm.
There was a point where we were saying if C is less than D, then we saw the path has gone to the right. So is there going to be another path where it now goes to the left instead of going to the right?
You see, from this basic block,
Yeah,
here there's no conditional. So from this basic block, control comes here.
yeah,
Okay. Then here we have, if C is greater than D, it would come this way and this way. Or if it's not, it would come this way and this way. But then here there's another conditional.
yeah.
Yeah. So then that's why we're just saying if I is greater than 10, control will go somewhere else. So basically trying to show, remember we're defining our points here and we're defining our path. Yeah. So for each statement, you see a statement that has a conditional can fork out two different paths depending on the result. Yeah. So from this statement, we would have two paths. This one either comes this way or this one that comes this way.
Okay.
Is that clear?
Yeah, that's clear.
Okay. So we're gonna come and look at this kind of optimizations. By now you already understood what they mean, what to call common sub-expression, constant propagation, etc. But we're saying now at the level of the CFG, we're at the level of the sub of the basic block, and also intra-basic block, between one basic block and the other. So redundant expressions. So now we use the notion of points. You understood what a point is? It's either between two adjacent statements or at the end of a basic, the beginning of a basic block and the end of the previous basic block. So we're trying to figure out how do we determine a redundant expression.
Or do you also need?
Yes, Robert.
I'm saying, do we also need to create a? I've seen that y times z was also repeated. When we're
Y
doing
times.
z, when we're doing m equals to 2 times y times z.
Uh-huh.
Later on in n, we're still doing y times z. So do you also need to remove that redundant expression?
Yeah, you could, but you see, okay, I guess yeah, because we're just, yes, you could do that. Because you find that 2 times y, you also have y times z, you have y times z. So you could actually store the value of y times z and eliminate it. So you see, I guess it depends on how you're doing this. Because first you're going to do 2 times y. Because remember, it's you're not going to first do 2 times y, and then if you start with y times z, then you're going to store y times z. You'll track y times z. But here we've started from left to right. Yeah, remember the left associativity and all that.
Yeah.
So that determines how you operate, which expression you first evaluate. So in this case, we've done 2 times y.
Okay. Thank you.
So some more terminology just around the point. So we introduce the notion of, because we're saying there's a point at which a value is defined, and then a point at which it is redundant. So we introduce the notion of what is called a kill site. Yeah. So these graphics just explain what's going on. So if this is our CFG, if we go step by step, we have C is equals to A plus B, B is A times C, I is 1, and then you come to this basic block. And then here we have Fi is assigned the value of A plus B. So the code optimizer first has to look for candidates, potential candidates that could be redundant. And you're basically going to list all the statements that are being computed in the path for this CFG. So you have A times Z, A plus C, whichever that are using variables, etc. Then now, for this particular statement where we have to now compute A plus B, we ask, has the value of A and B been modified between this point and the point that was defined? So you know this is the definition set for A plus B. There has been no, at any path over here, the points over
example, my symbol table, when it first passes, it builds all the nodes as raw as they are, but they haven't been optimized. So during this optimization process, will the value of those nodes be also compacted downwards?
Yes, depending on at what level you're doing the optimizations. You remember when you're doing target code generation, it still references a symbol table, isn't it?
Yeah.
Yeah. So if you do the IC optimizations and they modify values of your variables, you have to update the symbol table.
Yeah, could you please repeat about the code optimization for the loops? Because I've gotten lost somewhere how the value is being updated.
Which one?
For the loop optimizations, the code motion.
The one we gave for the code motion.
Yes, please.
Uh, this one. This one. Or which
No,
one? This
no,
one.
the next. Yes, this one. Because I'm getting lost where the value is being updated for the T1 because it would need to be like reduced. So if it's taken outside, how is it then updated?
What we've not expounded is this. So of course in the body of the loop there must be a statement that changes the value of I.
Oh, okay, thank you.
Yeah, we've not expounded this. But of course it's taken that of course the body of the loop must modify one of our conditional operators. Is that clear?
Yes, thank you.
So we're here. I was basically saying we've come to the conclusion of the course. I hope now if anybody asks you what is compiler design, you have a very good answer. You know what the process entails. For each stage, you know what language representation formalism we have, from DFAs for the scanner to the CFGs for the grammar and the corresponding pass trees. And then we have the notion of the data structures for the address and the address locator and everything for the IC to come up with the target code. Then you understand what the optimization is all about, why we do it. It's optional, but why it's important to do it, and the complexity of actually designing a compiler. Yeah, I think you've done a bit. That's why we just give you a very small what we're calling a mini grammar. But now you can imagine coming up with a compiler for one of your favorite languages, like Python or C or Kotlin, whatever. It takes a lot, and there's a lot of research that is done. There's a lot of programming. There's a lot of testing that is done before we can release a compiler for a new language. First, come up with the language, and you have ever asked yourself, why do we have new generations of languages? Yeah, there must be something that the people inventing these languages are trying to plug from the existing languages. Maybe you're saying this language is just really catering to string manipulation. That is going to be your focus, etc., etc. Right? And so the whole thing is first you figure out what are the unique features of the language, express that in a grammar, and then build the compiler for that language, and then figure out how you target it to different architectures, because you don't want a language that only works for one architecture. You want it to work that people are not limited, so they can. Because for most of these languages, there's what is called network effects. That something is only valuable when it's being used by many, many people. Yeah. So when you have a programming language that's used by two people, portability, developers, effort is not worth it. Yeah. But the languages that really thrive are those that are taken up by the community, and there are a lot of updates, there's a lot of improvements. And to get to that level, then of course every aspect of that language has to be top notch, including the compilation process. Yeah. So maybe just as a point of discussion, you all have learned how to program in very many different languages. So if I was to ask you to compare your most favorite language and the one that you hate the most, what result would you give for that analysis? Devin, can I start with you? Okay, good. You didn't put up your hand. Okay, go ahead, Devin.
Okay, go ahead. Actually, okay, I'm not gonna lie. I know it's all religious, but I hated C from inception. And everyone knows I'm more of a Python guy. But I've come to appreciate static typing. I'm not gonna lie. Um, so, and even Bentley introduced me to G. So, what I've appreciated from compiler design is that Python just gives you the overview of experimenting or working with the data types, but not the addresses. despite the fact that Python is not statically typed, you can do it,
Oh,
but yeah,
yeah.
yeah.
Okay, so that's been good insights for you. And that explains, despite C is actually a very solid language, it's very hard to learn.
Yeah.
And I also I hated to learn it when we had to read it hard there because remember you're getting lost and you're having to do memory allocations and all those bits and you're like, why do I have to do this?
Yeah.
But you can see what it means even for the compiler. You know, they're almost pushing a bit of the hard work to you as a programmer, but then it gives you very efficient code and very good to execute and everything. Yeah. So in terms of compile time, how would you compare C and Python? I've never
Um,
compared.
Python is fast, but I know C is much faster because it works close to the bare metal.
Mm,
Um, like for example, the mini compiler you made us build. I ran at 30 from our language. I ran at 39 statement, and it compiled in under a second. And I imagined that this is Python running on top of a C interpreter.
yeah,
So
yeah,
if I built this in C, it would be much faster.
much faster. Yeah. Okay, really good insights. Anybody else who wants to share their insights? Alex, what do you have to say? Okay, Roman, you can go first. I
Okay,
saw you.
yeah, right.
Okay. I was just saying, maybe my insight is from JavaScript, because in JavaScript it feels like you can do anything. You can add objects to strings, you can add strings to objects, numbers to objects. So I think seeing how, when we're making our compiler, how you define what things you can add to what kind of things, it made me appreciate languages like C more. Because in JavaScript you can get very crazy errors. Because maybe you've added null to an object and that gives you the number one for whatever reason.
Yeah.
Yeah.
And I hope now you actually even appreciate like the error messaging. Yeah. It's by the time the compiler tries to give you the exact error, you know, you keep having to tweak something to get a more meaningful error, you know, to try and see what really is wrong with my code. So the more, and I think that's usually the trade-off. Remember, the next slide actually was on why do we even need compilers? Yeah, and I'm basically saying you have a high-level language, and why do we need a high-level language? It's easier for the humans to work with a high-level language. Yeah. And there's been a lot of effort to try and simplify languages so much that you don't need so much effort to actually code. But what that means is that now the effort, the simplicity you're giving in the high level language results in a much more complicated compiler. Because now you're so far away from target code, you have to use the compiler to bridge that gap. So better for humans, but tougher for the compiler designers. Yeah. Alex or anybody else who has something to share?
Yeah, okay. All right, for me, I love Java because I've developed using it for many years because it's basically, it actually was the more like the enterprise language. All right, yeah, for me because it had, has automatic memory location. I don't have a problem with C, but I don't like it very much because it requires you to do your own memory management, and it's also not, it's more like procedural and it's not object oriented, so you end up writing programs which are full of security holes, and they are really not, they are really not secure. Yeah, so but Java has all these, and it's kind of manages all those things for you. Yes, and makes also the development speed very like quick, so you don't have to think of this, what did I do wrong, and all that. Has garbage collection and all that stuff. Yes. Yeah.
Okay. I like the insights that you have. But I think the question here, why is C still a very major, like, you know, like because of us, all of us, I guess, drive. We're being told between driving a manual car and an automatic. And then those guys who say if you're driving automatic, you're not really a driver, you know, that the real driver is that one who can balance the clutch, I don't know, and what.
Yeah, I would also go with that because I love driving manual cards. So
you
like
also-
you are given that full control. So it's not really you don't relinquish that to something else. But then again, at what cost? Because if you are to like come up with a compiler using C, would still do it, but then at what cost? Time and everything. Something will just break, and you know some of those examples of strings you give someone to test, they just break the whole thing, and you had already tested. But then you are given something like those strings you generate just breaks the whole thing, and you had done your test and everything. But but if you develop it using a different language, it's going to handle most of those things. Yeah. So for me, it's at what cost? Yes.
Mental health muhimu.
Okay, mental health. I've seen Adrian talking about it with more greater responsibility. With greater, what did you say? With greater freedom comes greater responsibility. Yeah, but I think we start to see, because like, why do you have, now when we're moving to self-driving cars, right? So you can imagine somebody who still wants to drive a manual car when the other extreme is cars that just drive themselves. Yeah. So it's always an effort to make life easier and easier for the masses, so that it's actually today Nopo can actually, like, you've seen kids who just program scratch, you drag and drop blocks, making it very easy to teach coding to very young kids. But then what that means in the background, somebody has done the heavy lifting to make that possible. Yeah. So it's always that trade-off between, are you going for the masses, or do you want to just have, those nuts at the back? Yeah. So I like all the comments that are coming in. The ladies are very quiet. Can we have some comments? Amina, Anita, what do you girls have to say? Eddie?
Hello.
Yeah.
Hello. Yes,
I
I have
will
a
try.
question. Yes, I have a question. As I've already implemented the parser, but I faced some challenges. Like, for example, initially our how they say the code we were using functions, but then we realized that for functions, okay, we ditched the functions, but I realized that for the functions, when it comes to how they call it, when it comes to passing the functions, you need something like an LL2. You need to look 2 steps forward in order to determine whether it's a function or not. This in the language is C. So what my question is, how can you like visualize an LL3 pass table or LL2 pass table? Does it contain the permutations, or it's just different? That's what I'm asking.
So remember we said the look ahead tokens. If you want to see further, you increase the window. Yeah. And it means that you'll be considering maybe 2 tokens, and I'd have to do the permutations. If these are if these are the 2 tokens I'm seeing next, what would come next? So it becomes much more complicated, and that's why I didn't ask you to implement that. Yeah. But then I like that you've appreciated the limitation of just 1 token of look ahead. And I'll tell you for a fact that most compilers do not use 1 token of look ahead. Yeah, because it's you end up having so many ambiguities. You don't know. There's so many possible paths, so it becomes more complicated. So they end up using longer tokens of look ahead at the cost of a much more complicated compiler. But because you're doing it once, then they just dive with it and they leave. Yeah. So for your project, don't try and make it that complicated. For me, what's most important is that you've understood the implications of a smaller window versus a larger window.
Okay.
Yeah.
Thank you.
But for the class project, I don't expect you to kill yourselves with more than 1 token of look ahead. Yeah, and that's why we said let's keep our grammars pretty simple. The idea was for you to just have a feel of what it takes to build actually a commercial compile. It is not an easy undertaking. Okay, I had asked for any ladies who want to share with us their experience in terms of the languages they like or dislike and why. Which one do you like and which one don't you like? Or Or you don't want to talk? Okay, fine. So just yesterday, interestingly, I met one of our former students. Yes, Eamon?
Hello, good morning. Good afternoon.
Good afternoon.
So, personally, I prefer Python. I think it's much easier to work compared to C and C++ because I interacted with C and C++ in first and second year mostly during schoolwork. So, personally, I prefer Python. I feel like the syntax is much easier to code with and use generally.
Okay. Okay. I think nobody seems to be voting for C or C++, but I think we understand why it exists and why we moved to these other languages. So I was just going to share, yesterday I bumped into one of our former students who finished maybe 4 5 years ago. And it was such an interesting conversation we had because he told me when he started working, he joined Amazon and he felt he knew nothing. Okay, I don't know, I'm laughing, but it was actually, it just continues to validate what I keep telling students, that we're in a field that changes so quickly. I can tell you guys, before you're done with your 4th year, you might be obsolete, you might be irrelevant if you're not keeping up to date with what's happening. Alex, you're laughing. It is so true. Like you and me, I'm on the verge of retiring. I don't think I can keep up with all the changes that are happening. So he told me, of course, he was a very good developer. I think he got a first class, a really good student, and he was very good in Python. And I'm not saying anything about Python. So he goes to Amazon, and believe it or not, everything at Amazon is based on Java. Everything. There's nothing they code any other language other than Java. It's only now they've moved now to Kotlin, right? So as much, and why am I telling you this? You have to have an open mind. Don't say me, I just love Python. Yeah? You have to be really good, Robert. Because I saw somebody saying JavaScript is the way to go. Amazon have already decided that is the way. But the most they've done now is move to Kotlin. So my challenge to you guys is try and figure out what are the languages that are gaining prominence. Today we're thinking about Python. Next year it might be something totally different. Yeah. And why at the university we teach you the principles, we don't teach you specific technologies, is that you're able to quickly learn something new on your own. Yeah. So, and I think we need to get this